We're going to move on to our second presentation now by Kevin Nuckolls on customizable, unconventional superconducting materials.
Excellent. Yeah, thank you so much for that introduction. I'd like to first start by thanking the organizers, particularly Carol, for really putting all this together, this wonderful symposium, and just send a very special thanks to Neil and Jane for not only supporting this research, but also being so welcoming to me this first year in Boston. So again, my name is Kevin Nuckolls. I'm a first-year Pappalardo Fellow here at MIT, working very closely with Joe Czajkowski and his group. And today I feel very fortunate to be able to tell you about not only the rich and vibrant physics of understanding superconducting materials, but also about a new and exciting opportunity that my teammates and I have uncovered in designing and customizing a new class of unconventional superconducting materials. So I want to start by reviewing a few of the most basic, most important properties of superconducting materials. When we think about these materials are extraordinary because they can conduct electricity without resistance. They do so without heat dissipation or energy loss. But in addition to this, superconductors also expel magnetic fields from their interiors. So I'm willing to bet that many of you in this audience have seen something in the news or read an article recently about the amazing promise of a potential room temperature superconductor, a material that would have these two properties at ambient pressure and 25 degrees Celsius. So these materials would be amazing for technological applications, such as the ability to transmit large amounts of power over long distances in the form of a new generation of superconducting power transmission lines. We would also want to use them in things like high-speed levitating train technology, which could revolutionize ground transportation. A lot of these applications that people talk about in these articles are a bit futuristic, maybe a bit speculative, but I would offer that actually these applications seem a lot less speculative when we recognize how superconductors have influenced much of our technology today and now, the most famous of which is our use of superconductors in MRI machines. It comes as a real surprise to me that superconductors have really enabled this tool that the healthcare system uses for making diagnoses without in use of invasive surgery procedures. In addition, superconductors form the working medium for an emerging landscape of quantum technology that has the opportunity to revolutionize how we transmit information securely and how we perform complex computations. And so to me, all this is exciting. All of these are worthwhile endeavors, but also all of these are stemming from a fundamental understanding in the properties of superconductors, a fundamental physics understanding in the properties that they have and how we can control those properties. This kind of speaks to the idea, as physicists, we want a clear, concise, quantitative description of our natural world, the world around us. And when it comes to superconductors, there are many different properties that we want to be able to explain, but we also want to be able to tune them for our various applications. And so this kind of motivates the research program that I've embarked upon, my teammates have embarked upon, as well as thousands of physicists across the world to understand these materials. So to me, superconductivity research is one of the most interesting, but also one of the most fulfilling subfields of condensed matter research for a couple of different reasons that I'll share with you today. The first is that superconductivity research has had some paradigm-shifting experimental discoveries that have really challenged what we believe is possible in nature. A really famous example of this is the discovery of high-temperature superconductors in the 80s. So before 1986, high-temperature superconductivity was thought to be impossible. We believed that it was exclusively a low-temperature phenomenon, existing below something like 30 degrees Kelvin or minus 240 degrees Celsius. So here I'm showing some data of a state-of-the-art superconductor at the time, a niobium-based superconductor, which shows this resistive transition at a respectable 21 Kelvin into this zero-resistant superconducting state. So this material was kind of the product of nearly a decade of research into trying to perfect this material, trying to optimize its properties. But all of this is kind of overshadowed by a landmark discovery of copper oxide-based superconductors. These are new superconducting materials that were relatively easy to synthesize, and within a few months, many groups had reproduced these awesome plots where we see superconductivity onsetting at something like 3 times the theoretical bound that was previously proposed. So although these kind of paradigm shifts don't happen that frequently in this field, I offer that they actually don't happen inconsistently, maybe something like 1 every decade. In addition, superconductivity research has had some of the most highly generalizable theoretical proposals that have had really broad-reaching impact across research fields. So a really famous example of this is the mathematical parallels that we've seen as physicists between our microscopic theory of superconductivity, our understanding of their properties and where they're derived from, and our developing theory of fundamental particles, which was largely developed in the 50s and 60s. So during that development, we came across this model, which we now refer to as the standard model of particle physics, which describes all of the fundamental particles in the universe that we've now observed and how they interact with one another. And it was really looking to insights, looking for inspiration in superconductivity research that really helped shape this theory as a whole. So eminent theorists like Yoichiro Nambu and Jeffrey Goldstone, these theorists were trying to answer questions like, how do fundamental particles interact with one another? It's clearly a question that lies significantly in the domain of high-energy physics and in particle physics, but these physicists were able to answer this by thinking differently. They looked at superconductivity research and thought about how superconductors become superconducting, how they transition into the superconducting state. Moreover, physicists like Phil Anderson and Peter Higgs were thinking about questions like, why do fundamental particles have mass? This is, again, clearly a high-energy physics question, but these physicists came to the correct conclusion, they came to the right answer, because they were thinking about how electrons, their energy levels are rearranged in a superconductor. So all of these theorists are really drawing inspiration from superconductivity research deeply from this kind of landmark, foundational result in my field known as the conventional theory of superconductivity. This was a theory that was discovered by Bardeen-Cooper-Schrieffer, who all share the Nobel Prize in 1972 for this discovery. We sometimes refer to it by their names, Bardeen-Cooper and Schrieffer, but we also refer to it as the conventional theory of superconductivity because it describes the vast majority of superconductors that we know of in nature. So this theory has many parts, many working parts, but it's actually relatively simple, and I'll try to work you through some of the general ideas of this principle. So the idea starts as follows. If I'm conducting electricity through a metal, something like an aluminum wire, then that electricity flows in the form of electrons, but those electrons move in a sort of uncoordinated manner. They're scattering off of one another, they're scattering off of these impurities found in that metal, and every time an electron scatters, it dissipates heat. It causes resistance in that wire. But if I take that aluminum wire and I cool it down to low temperatures, I find that aluminum wire will enter the superconducting state, which is a new phase of matter. So in a superconductor, electrons flow as a collective state. They flow coherently, they don't get in each other's ways, they don't scatter off of these impurities, and they do so by the insights of Bardeen, Cooper, and Schrieffer because electrons don't flow individually. They don't flow alone through the superconductor, but they form in these pairs of electrons, which we now call Cooper pairs. And the idea is that these Cooper pairs abide by very different laws of quantum mechanics than single electrons, namely that Cooper pairs are rather gregarious, they're kind of friendly, and they can cooperate in this collective phase of matter, whereas electrons are getting in each other's ways, and they don't want to produce these kinds of superconducting states. I'm sweeping a lot of the details under the rug. I think that this is not particularly relevant for this talk, but I do want to give a feeling for why these Cooper pairs would form in materials, because this gives us a feeling for why we should even expect superconductivity in many metals that we probe as condensed matter physicists. This comes as kind of an opaque or maybe a puzzling challenge to someone who hasn't studied this theory because these two electrons, they're both negatively charged. We know that like charges repel one another. And so at first, we wouldn't believe that they should kind of pair up with one another in this superconducting state. But the insights of these authors was that electrons don't live in a vacuum in materials. They live in an atomic lattice. And that lattice is elastic. And so that lattice deforms in ways that mediates attractive interactions between these electrons. This is the real crucial ingredient for conventional theory of superconductivity, and it explains why we would believe that many metals would support superconductivity when we cool down to low enough temperatures when this interaction scale becomes relevant. I want to emphasize that this is a real triumph of condensed matter theory, that something like 99.9% of all superconductors we've ever discovered abide by the laws set by the conventional theory of superconductivity. And the number 99.9% for kind of everyday use, we wouldn't really even consider this as different than 100%. Imagine reading on the backside of maybe your disinfectant spray or on your hand sanitizer that it kills 99.9% of germs. We wouldn't really think twice about this. But the thesis of today's talk and the dedication of thousands of physicists' careers to this effort is that this 0.1%, these so-called unconventional superconductors, these are really important. And namely, they're important because they're record-breaking by every metric. That they survive to the highest temperatures, the highest magnetic fields, and the lowest densities that we measure in these systems. So they're really robust superconducting states. I really want to motivate this kind of graphically with a very famous plot in my field where we'll plot a series of transition temperatures, critical transition temperatures on the y-axis, which gives me a feeling for the energy scale guiding superconductivity. How strong is superconductivity in these materials as a function of the year at which that superconductor was discovered on the x-axis. So over the many decades, we've seen many low-temperature superconductors, many of which are described by this conventional theory of superconductivity. This is because this conventional theory is a very weak coupling theory, that electrons don't interact very strongly with their lattices, and so these energy scales are actually rather weak, and they appear only at very low temperatures. But you'll see graphically that there are sharp departures in this timeline in the form of a series of unconventional superconductors, the high-temperature copper oxide-based superconductors, and the high-temperature iron-based superconductors. These show show kind of fissures in the phase diagram, fissures in the timeline, and they're guided by much larger energy scales related to magnetism, related to the spin degree of freedom of the electron, which can be very large. By now, we've seen unconventional superconductivity across many material platforms over the decades. We first saw them in these cerium-based compounds in the 70s. In the 80s, we uncovered them in uranium-based and copper-based systems. In the 2000s, we found them in iron-based systems. And most recently, we've seen them in even purely carbon-based systems. So this lattice on the right side is the most eclectic of the ones that I'm showing right here. This is magic angle twisted bilayer graphene. This was discovered right here at MIT in 2018 by Pablo Herrera's group. And I spent much of my PhD trying to understand the microscopic mechanisms of this beautiful unconventional superconductor. So I show all these materials mainly to focus on the fact that unconventional superconductivity is appearing across a wide variety of material platforms. They're very different than the known methods for producing superconductivity based on BCS theory, but in some ways they show some similarities among them. So you'll find that material properties across material platforms show some similarities, beckoning some notion of universality in these systems, beckoning the notion that we would be able to uncover kind of guiding principles that would help us understand these materials. In addition, kind of bringing it all back to the beginning of this talk, there's this holy grail of condensed matter physics, of discovering a room temperature ambient pressure superconductor, which I argue is only going to be achieved, this technological impact of these materials will only be achieved if we really understand from a fundamental level unconventional superconductivity, because by far these are our best candidates for the job. And so this all motivates a major research effort here at MIT with my teammates and I. We're trying to design new materials that are highly conducive to unconventional superconducting states. New materials, new examples give us a number of different opportunities. The first is that new materials allow us to kind of test existing theoretical proposals, kind of disentangle competing mechanisms, or to identify what might be guiding superconductivity at kind of borderline cases. In addition to this, kind of a more broad perspective is that new materials generically give us new and unexpected physics. It's kind of the mantra, the research program of Professor Emeritus Arthur von Hippel, who discussed this as a reasonable and very worthwhile endeavor, because these paradigm shifts that I discussed at the beginning of the talk really came from new materials that were introduced into the community. So once we have all these new materials, we'll want to be able to characterize them, but we'll want to characterize them holistically. We'll want to have many orthogonal probes to understand all of the properties of these superconductors, because we want to be able to characterize how they violate the conventional theory of superconductivity in some detail. So we'll want to focus on materials that are highly compatible across all of our material techniques, and this kind of allows us to draw a lot of inspiration from nature through its detailed study. There's this story that I really like about this very famous Impressionist painter, Pierre-Auguste Renoir. The story goes that Renoir was once asked why he leaves his studio and goes out into nature to paint many of his works. And Renoir gives a very beautiful answer. He says that if he were to sit in his studio and try to paint leaves, that his mind's eye could only think of something like 10 or 12 different examples, something small. But if he goes out into nature, that nature has 10,000 examples awaiting his detailed study. So in some ways, experimental physics has some of these parallels, that if I were to sit in my studio apartment and try to think of new theories of superconductivity, I'm not sure I could think of really one that would carry any water. But my teammates and I are synthesizing new materials, we're coming up with new examples, and we're really using these as distinctive tools for getting at some open questions in the field of unconventional superconductivity. So this is the research program. I want to shift gears a bit and talk to you about how we'd actually go about doing this research. So particularly, we'll focus on how would we actually go about synthesizing new superconductors, growing new materials. So at this point, it's a really good time to take a page out of Nature's book and to look to nature for some inspiration. So these are some photos that I took at the Mineralogical and Geological Museum at Harvard, just up the street. This is a really beautiful exhibit that I visited a couple months ago. They have something like 10,000 specimens to look at, all different crystals, and largely grown by Mother Nature using the same technique. So the idea is that Mother Nature grows new materials by using high temperatures and high pressures found below the Earth's crust. She combines natural, chemical, elemental sources, but she does so over very long time scales. So we're growing these materials from atom by atom into these macroscopic kilogram-sized crystals. So in the Czochralski lab, we're doing very similar things. We're emulating nature and using these high-temperature furnaces that get up to something like 1,200 or 1,500 degrees Celsius. If you were to put all your chemicals into these high-temperature furnaces, they would all just oxidize, because we live in a very oxygen-rich environment. And so in order to protect our chemicals, we seal them up into these double-sealed quartz tubes here. So all my chemicals are sitting in here, and this is evacuated, so there's no air in this environment. And when you use the right chemicals and combine them over the right temperature profile, then you can grow beautiful single crystals, which albeit are much smaller than those found in nature, because I had something like 2 weeks to grow these, and Mother Nature took millions of years to grow them. So in preparing this talk, I actually got some really awesome questions about this middle image right here. So here are all my chemicals down at the center, and it's sealed, double sealed in this quartz ampule. And so a natural question that I got was, how do you actually put the chemicals inside the quartz tube? How do you get them inside for this chemical synthesis process? And so the answer to this is that we use an oxyhydrogen torch. Oh, my video didn't work. Let's try. There we go. Yeah, so this is a day in the life of an experimentalist. I'm using an oxyhydrogen torch with some safety gear. So this is fireproof gloves and coat. I've got a face mask and goggles that are not unlike the ones that you use for solar eclipse observing. We're burning tanks of oxygen and hydrogen at thousands of degrees Celsius. And I'm kind of necking the tube. I'm collapsing it while I'm pumping out all of the air from the system. So all my chemicals are in my hand, and I'm trying to homogeneously collapse it in on itself until it gets all molten so I can just pull off the connection. It's a really awesome way to do this. It takes a lot of practice, a lot of finesse, but after a while, once you break a bunch of tubes, you can get really good at this, and it feels very good. So another aspect of this photo was that another question I got that was really natural is that once you've spent all this time trying to prepare all these superconductors, how do you go harvest your precious chemicals? How do you actually access those crystals? And the answer to that is that we use a hammer. The timing on this was so much better when I had it with my clicker. That's okay. That's okay. Okay. So at this point, I want to shift gears and talk really concertedly about my own work, my team's work, and how we're trying to answer some of these open questions in superconductivity research using these new materials. So to get us started, here's the periodic table of elements. A really natural place to find some layered superconductors, two-dimensional superconductors, is that we look for these transition metal dichalcogenides. So these are made from a 2-to-1 ratio of chalcogen atoms like sulfur, selenium, and tellurium with these transition metals found on the left side of the periodic table. A really prototypical example of this is niobium disulfide. This is kind of a place to find materials that are relatively clean. They're kind of model systems for understanding quasi-two-dimensional superconductivity. And they've been studied for many decades because they're a bit tunable. We have some nice experimental tuning knobs for understanding their properties. But our team has discovered a new way to grow materials that are related to the structure by incorporating a new class of alkali earth metal elements. So these work their way into the lattice, but they do so in a kind of unusual way that gives us a new tuning knob on the properties of superconductivity. So here's one of those transition metal dichalcogenides. This is niobium disulfide. These niobium orange atoms are in the center in this corrugated lattice of sulfur atoms. These are superconducting layers where the electrons spend most of their time, but electrons sometimes hop across this so-called van der Waals gap, which separates the superconducting layers. That kind of thwarts the two-dimensionality of these materials. But when we incorporate new atoms, these alkali earth elements, they form this layered, ordered structure that separates superconducting layers. So this makes the lattice far more two-dimensional, much more emulating some known structures for unconventional superconductivity. But in addition to that, I have a lot of control over this spacer layer chemically. So I want to emphasize that these are really awesome materials to study for unconventional superconductivity because they have many of the essential ingredients that we've seen over the decades have given us unconventional superconducting states. They're generically really clean metals by some miracle of the chemistry that we're using to produce these materials. But in addition, they're highly two-dimensional. These layer-separated spacer layers are kind of separating all of the electrons in one layer and making this system act like a monolayer superconductor. In addition, I have a lot of degrees of freedom in being able to customize superconductivity, customize this spacer layer without really affecting the pristine layer of superconductivity. So we're doing so in proximity, but in a bulk system. So I have a lot of control over the chemical environment at which superconductivity lives in, but also a rich variety of lattice geometries that we hope to tell the world about publicly in the next year or so. At this point, another thing that we really love about these materials is that they're really amenable to a holistic approach to condensed matter physics. So we have a lot of different probes, material probes for understanding superconductors, some of which probe thermodynamic properties. So we want to understand the transitions of these materials into their superconducting state. And we want to understand the magnetic textures in these systems using some magnetic probes. these are kind of long-standing techniques that help us gain insight into the properties of these superconductors. But on the other hand, these are van der Waals materials. And so they're compatible with some of our 2D device probe geometries that were developed to study other 2D materials, like graphene or boron nitride. So we're exfoliating these and putting them into micron-scale devices to probe their superconducting behavior at this length scale. I want to leave you with this picture of many different superconductors that we're working with. These form a really diverse and variable class of new materials, and we love how tunable they are, but also how amenable they are to being used as tools for answering some long-standing open questions in the field. So with that, I'd like to thank you for your time, and to thank the people I work with, particularly Frank, Alan, and Roe. The four of us are working in kind of all different directions in this emerging field in the lab of Joe Cikelski. I'd like to thank many sponsors of this research, and particularly the Pappalardo Fellowship for making all this possible. Thank you.
Kevin, thanks very much. OK, we're open for questions. Neil?
I have just a curious one. In superconductivity of these lattices, is the superconductivity directional? I.e., if you stack these layers up in a sandwich, is it superconductivity in a particular plane, or is it into the plane?
It's an excellent question. So yeah, the question is really focusing on the fact that these are layers of superconductors, but there's no superconductor between these layers. And so when we probe these systems, we measure superconducting properties in all directions. So we find the very good metals in plane, they become superconducting, but out of plane, we also can measure supercurrents in some settings. So it's a question about length scales. It's like how long a distance do I have to leave the superconductor before I'm no longer superconducting? So I think that being able to measure these properties out of plane versus in plane gives us insights into these materials, but also shows that they're isotropic. On the other hand, though, there are many proposals, really exciting proposals for directional superconductivity, some of which I believe that we can access in these materials. So there's this notion of a superconducting diode. This is an idea of a material that would conduct electricity dissipationlessly in one direction, but it would be resistive in the other direction. These have been seen in a couple of materials now to date, but I believe that there are versions of that type of physics that could be realized with this architecture. And so we're thinking about these ideas. Yeah.
OK, other questions? Yep.
Test it, are you able to then go to a theorist and make a model, or is it a kind of situation where you're like, the transition is 100 Kelvin and I don't really know why?
It depends on, yeah, what project. So definitely there are situations where experiments will show you something really paradigm shifting and you don't know how to address it. But in a lot of situations, we kind of think of the relevant energy scales at play, and we can come up with some sort of phenomenological model at first that kind of gives us an understanding of some competing energy scales that would provide us one type of superconductivity versus another type of superconductivity. Other type of modeling that you can do are electronic structure calculations. So all superconductors are derived from a metallic state, and oftentimes that superconductor derives some of its properties from the exotic or naturalness of that metallic state. And so oftentimes we'll use condensed matter probes to probe the metal from which superconductivity comes from, and we can do a lot of modeling in that scenario to figure out what do the electrons want to do before the superconducting state imposes itself. So I think it's kind of across the wide spectrum. It really depends on what type of question you want to answer, how difficult is it. Yeah.
For these, like for this one you
Yeah.
here, do you understand like the mechanism for the pairing version?
To some aspects, but not all the understanding. So I think that, and it strongly depends actually on the material within this class. So there we see a lot of different types of superconductivity, some of which are much more easily explained than others. Maybe I can say, I have one backup slide that I'll just show real quick. Yeah, so this is one of the first compounds that my advisor and a former grad student had discovered in a compound known as barium niobium sulfur. So this is a two-dimensional layered system. So these are niobium disulfide layers separated by barium niobium sulfur. And it was predicted long ago that superconductivity should appear kind of homogeneously in the BCS theory, this conventional theory, but an in-plane magnetic field could drive a state that is highly unconventional, that it shows this kind of striped behavior. And in a situation where we have clear and quantitative predictions for this theory. So a phase diagram plotting the critical trend field of the superconductor as a function of temperature, they see characteristics of a phase diagram that looks very similar to theory driven by this kind of phenomenological model. We're not thinking about any of the atoms or any of the irrelevant small energy scales, but thinking about just generally what happens to a superconductor in an in-plane magnetic field. Yeah.
Salvo, can you use the mic over there?
Yeah, so thank you. I have actually a comment and a question. A comment is related to physics. Every time I read that something kills 99% of the germs, I tell myself, so many of them. You know, so it's not very reassuring. Anyhow, so my question was actually kind of the, complement of the last one. And so can you tell me what role theory plays? So for example, if you go in your plot that shows the breakthrough of temperature as a function of time, can you quickly guide us through the breakthrough and tell us which one were people saw coming based on theoretical ground versus which one were surprises, people just picking elements from the periodic table or anything in between? Thank you.
Yeah. No, it's an excellent question. I think it's, definitely a kind of a case-by-case basis that we should talk about these. But generally, I think that a lot of these discoveries, particularly the copper oxide-based superconductors or the iron-based superconductors, in kind of thinking in hindsight, people give explanations as to why they were walking in this direction. But often the mechanics of the superconductor don't operate the way that they think it does. So it wasn't that there were physicists working on these copper oxide-based superconductors that had some notion that its lattice should provide high-temperature superconductivity. But I don't know if that idea has really panned out. And so I think a thing that I can say pretty confidently is that when finding new materials and kind of giving people early examples of something that is tantalizing, something like 35 degrees Kelvin, then experimentalists jump after this and can very rapidly reproduce this material, but also find new related materials. It gives kind of an opening for experiment, and then very suddenly an emerging community forms around this that is a concerted kind of interplay between experimentalists and theorists trying to understand subtleties to this argument or understand the validity of available theories. So. An excellent perspective on this.
No editorial comments from the audience, please.
We all need funding, right?
The speaker was reserved to make the side remarks. Okay, so it's Kevin, I have a question for you. So it's two parts. So you were telling us about these tunable lattices.
Yeah.
So can you tell us about what are the parameters that you want to be able to tune that you're able to now, and why that's important? Yeah. And then the second part of my question is, are there parameters that you wish you could tune, but that you haven't figured out how yet?
Sure. Yeah. So I think that tunability generally, I think to me the most important aspect is it gives us a firm knob to tune to understand the connection between a property and its macroscopic properties. So the tuning of the lattice allows us to kind of tune small relevant energy scales, things like an energy scale called spin-orbit coupling. This is an energy scale that's found when using large atoms like tantalum in your crystal that kind of couple the spin degrees of freedom with the orbital dynamics of that electron. So in being able to customize these systems, we can tune some of these parameters somewhat, but I think we're also kind of just on the precipice of understanding the influence, particularly of the lattice that we're finding in these spacer layers and how it imprints itself on the superconductor. So there's some work. Maybe I can show another. So here's a really awesome example of that. This is strontium tantalum sulfur. This is a compound that was posted on arXiv a couple months ago. The idea is that this material has a very long wavelength incommensurability, not unlike something found in other incommensurate lattices like the high temperature copper oxide superconductors. So you see this kind of rumpling of the superconducting layer in this lattice in a way that influences transport phenomenology. So here, maybe focus on this plot particularly. The measurements are that we're plotting the critical current, the supercurrent through the plane, so out of plane between layers, as a function of the in-plane rotation angle of the magnetic field. And you can see that because the superconductor has these kind of stripes in its structure, you can see that it imprints itself on some anisotropy, this kind of lobe-like or oval-like parameter, that the superconductor is stronger in one direction and weaker in another direction. And so by tuning this, I mean, this is kind of surprising because we have some ways of studying this monolayer superconductor tantalum disulfide, and it's highly isotropic. And so it's really the coupling between these lattices that has endowed this material with that kind of aspect. So I think we're kind of thinking about other ways that this might imprint itself, and generally we're trying to tune that spacer layer to impart different tunable anisotropic or robust properties in the superconducting state. Yeah.
Okay, time for one more question. Use the speaker, thanks.
I have a bit of an impossible question. When you initially showed all of these new discoveries, was it accidental? What do you just go in the lab and add one more secret ingredient? So how do you go about maybe trying something new?
No, that's a good question. Yeah, so I think trial and error is a good way to find good science, but it's also, I mean, a lot of this is kind of leading off of design principles. So I think that my understanding of this first example, barium, niobium, sulfur, is that group members were trying to grow one material, and they found this other material that seemed to show superconductivity. So studying that superconductor, figuring out its properties and how it relates to the lattice is really important. But more recently, we've been taking some of the chemistry design principles of how this crystal grows and testing a lot of phase space to kind of understand how we can affect the structure, affect this spacer layer. So it's, in some ways, it's random, it's fortuitous, it's opportunistic, but in some ways, we're also understanding that things make sense in a global phase diagram. And so I think that it comes slowly, definitely not at the point of the first discovery, but over many years and many great lab mates, particularly who are working in different directions, we can kind of all coalesce on some understanding of these systems. Yeah.
Okay, thanks, Kevin, again.
Thank you.